Hi, this is a video abstract on the urban positioning 3D GNSS using the dual frequency pseudorange measurements from the smartphone. My name is Haifeng Ng. The urban GNSS positioning is difficult because of there is a NLOS reception and the multipath effects. And we believe that the 3D GNSS have been used for different commercial applications such as the shadow matching that using the satellite visibility and the Raytracing GNSS using the pseudorange measurement. And they have different nature on their performance. So the shadow matching have a better across street direction, and the ranging-based 3D usually perform well on the along street direction. Therefore, the combination of it can maximize the positioning performance. However, if mainly handling the NLOS reception, the multipath effects is still an unknown during the positioning. Therefore, the L5 signal can play a role to mitigate the multipath effects. And because of the high tripping rate and narrower correlation peak, it can also solve the NLOS problem with the 3D GNSS because it can isolate the NLOS bias, which become more precise. Therefore, this study going to mitigate the NLOS reception and the multipath effects simultaneously by combining the 3D GNSS and the L5 measurements. And we are going to also comparing different receiver clock modeling approach and integrating the shadow matching and the ranging-based 3D GNSS. And go to the methodology. After we generating the sky mask on the online stage, after we get the initial position, we can distribute the candidates. And at each candidate, we can estimate the satellite visibility for shadow matching and modeling the pseudorange as well as the NLOS correction. Then we can compare the prediction and the measurements to score the candidates and output the position. And the L5 measurement can play different roles, such as for the measurement selection, we can replace the L1 signal with the L5 signal and give a higher weighting to it. And for the receiver clock estimation, we are going to use a particle-based weighted square, and we are going to integrate the solution and comparing their performance. We have done several experiments with the smartphone inside different scenarios in Hong Kong. And we found that most of the positioning area are within 10 meters averagely. And if we look at the L5 and the L1 measurements, for a multipath labeled satellites, the pseudorange area of the L5 signal is much smaller than the L1 signal. And if we counting all satellites inside different experiments, it's shown that the L5 signal have a better pseudorange quality than the L1 signal. And if we also looking at the receiver clock estimation, we found that the inter-constellation clock offset is benefits the ranging-based 3D GNSS, and a particle-based weighted square is more robust comparing to a single difference when we estimate the receiver clock offset. As a conclusion of this study, the integration of the shadow matching and the ranging-based 3D GNSS can improve the positioning performance. Incorporating the L5 signal can provide a more stable positioning for the 3D GNSS. And we propose to using a particle-based weighted square with inter-constellation offset to estimate the receiver clock. And we believe that the 3D GNSS with L5 signal is the future for smartphone application, which can provide a better initial guess for a higher precision application. And that's all for my presentation. If you are interested in our study, welcome to check out the full paper.